Welcome to a webcast produced by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Numeracy series and concerns the different kinds of numbers. This guide introduces, in an historical perspective, the different types of numbers which mathematicians use today and the various names and symbols which they are given. All of us first experience the concept of a number when we are very young in relation to counting objects. You can easily start to write them down. 1, 2, 3, 4, 5, and so on. These numbers are usually called the natural numbers by mathematicians. They can also be thought of as the counting numbers, although no definitive convention has been agreed. They can be thought of as the numbers of objects in a collection. These numbers began to be written down in a symbolic way by the Egyptians and the Babylonians, circa 3000 BCE, mainly as a way of bookkeeping. The Egyptians used a system of base 10, identical to us today, and the Babylonians used base 60, remnants of which exist in our measurements of time and angle. Many properties of natural numbers were deduced by these people, and some astounding records of their achievements still exist today. For example, the Rind Papyrus, circa 1650 BCE. You may notice that 0 is absent from the list of natural numbers, and although the Egyptians knew of its existence, 0 was not necessary for calculations involving amounts. It was first written in its present form in Cambodia in about AD 683, and it was around that time that the great Indian mathematician Brahmagupta wrote the arithmetical rules of 0. If you include 0 in our list of natural numbers, you get the whole numbers. 0, 1, 2, 3, 4, and so on. Negative numbers were first used in China during the Han Dynasty, from around 202 BCE to 220 AD. For many years, results which were negative were considered absurd. Again, it was Brahmagupta who wrote down the rules for their manipulation. If we consider the negative analogues of the natural numbers and add them to our description, we get the integers. -3, -2, -1, 0, 1, 2, 3, and so on. The set of all integers is denoted by the symbol Z, from the German word Zahlen, and contains all the whole numbers. Before the discovery and acceptance of negative numbers, other types of numbers were known. When numbers are divided, not all answers are integers. For example, 3 divided by 5. And so a new type of number was required, the fractions. Mathematically, fractions are known as rational numbers, and strictly, they express the ratio of two integers. The denominator cannot be 0. The set of rational numbers is given the symbol Q, as in quotient. Certain rational numbers, those with the numerator of 1, unit fractions, and also 2/3, were known to the Egyptians. Also, a limited number of fractions were used by the Babylonians. A more general treatment evolved in Greece and is encapsulated in Book 5 of Euclid's Elements, circa 300 BCE, although no contemporary copies exist. The set of rational numbers contains all the integers along with the so-called terminating decimal numbers, such as 3.6 and 8.72, and the repeating or recurring decimal numbers, such as a third, which is 0.333, continuing on forever. The Greeks also knew of another type of number that didn't fit the patterns described so far. To the Greeks, if two numbers had a common measure, then the ratio of these numbers was a rational number. If not, then the number was thought to be incommensurable. Many such incommensurables appear in the Greeks' exploration of geometry. For example, consider the length of the hypotenuse of a right-angled triangle whose other two sides have a length of 1. The theorem of Pythagoras tells us that the length is √2, which was proved by Hippasus of Metapontum in about 700 BCE, not to be a rational number. Euclid coined the term irrational for such numbers, and they form a set completely apart from the rational numbers. Irrational numbers form non-terminating decimal numbers which never repeat themselves. Many irrational numbers form solutions to algebraic equations with rational coefficients. For example, one of the solutions to the equation x squared minus 2 equals 0 is the square root of 2. However, there are many irrational numbers which do not fall into this category, and these are called transcendental numbers. Many of the most famous numbers, for example pi and e, are transcendental. Showing if a number is transcendental or not proved to be difficult, and it wasn't until 1844 that Joseph Liouville wrote down one. E was shown to be transcendental in 1873 by Charles Hermite, and pi in 1882 by Ferdinand Lindemann. Together, the rational and irrational numbers make up the set of real numbers, which is given the symbol R. When you draw a number line, you are sketching a visual representation of all the real numbers. In the Renaissance, a solution to the general cubic equation was found by Girolamo Cardano, 1501 to 1576, which implied the existence of a new type of number. It was thought at the time that square roots of negative numbers were impossible. After all, what number multiplied by itself equals a negative number? But it seemed from Cardano's formula that these numbers were necessary in order to complete certain calculations. The book Algebra, written by Raphael Bombelli, 1526 to 1572, was the first place to define numbers that were neither positive nor negative, the complex numbers. Complex numbers rely on the premise that the square root of a negative number does exist, and defines the square root of minus 1 to equal I as a building block. For example, the square root of minus 7 equals the square root of 7 multiplied by the square root of minus 1, which equals the square root of 7 times I. This notation was due to Leonhard Euler, 1707 to 1783. Many of the great mathematicians in the 18th century worked on complex numbers, and their discovery and acceptance proved revolutionary. A complex number comprises two parts, one that is a purely real number and one that is a real number multiplied by I. If the purely real part is 0, then the complex number is called imaginary. Of course, if the number multiplied by I is 0, then you get a real number. This shows that the set of complex numbers includes the set of real numbers. The set of complex numbers is given the symbol C. Today, mathematicians consider numbers to be divided into the following sets: N, the set of positive integers; Z, the set of integers; Q, the set of rational numbers; R, the set of real numbers; and finally C, the set of complex numbers. Any number you can think of falls into one of these sets. Further guidance and information. If you have any further questions about numeracy or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor, or make an appointment to see a learning enhancement tutor in the Dean of Students office. You can telephone 01603 592761, email dos.help@uea.ac.uk, or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills. This guidance is one of a series on mathematics produced by the Dean of Students office at the University of East Anglia.